All right, let's talk about energy. It's this invisible force that literally powers everything, right? From our own bodies to entire cities. But, and this is the big question, do we actually get how it works?
So let me start with a question for you, a little puzzle. Imagine you're driving. If you double your speed, say from 30 miles per hour to 60, you'd probably guess that a crash would be twice as bad, right? Well, nope. It's actually 4 times worse. 4 times! So what's going on there? The answer is all about the fundamental physics of energy, and that's exactly what we're going to get into.
Okay, so let's get right down to it. What even is energy? You'll see the textbook definition here, the ability to do work or cause change. Now, in physics, work doesn't mean your 9-to-5 job. It's about using a force to literally move something from one place to another. So really, energy is just the power to make stuff happen, to make things move, heat up, or change in any way. You could almost think of it as the currency of the universe.
So to really wrap our heads around this, we have to start with where energy is hiding in the first place. That brings us to our first section, the hidden force.
It turns out, energy isn't just one thing. It comes in a whole bunch of different flavors, you know? It's stored as chemical energy in the food we eat, as thermal energy in a hot cup of coffee, even as nuclear energy locked inside atoms. The list is pretty long. But to solve our car crash puzzle, and frankly, to understand most of what goes on around us, we really only need to focus on 2 big ones, the energy of movement and the energy of position.
And that's our next section, energy in motion in place. This is where we're going to find the answer to that car crash question.
Okay, first up, kinetic energy. This one's pretty straightforward. It's the energy of motion. Anything that's moving has it. A planet going around the sun, a baseball flying through the air, even you just walking down the street. The basic rule is simple. The more something weighs and the faster it's moving, the more kinetic energy it packs.
And believe it or not, there's a really simple but, incredibly powerful equation that tells us exactly how much energy we're talking about. It says that kinetic energy is half the object's mass times its velocity squared. And that last little word, squared, yeah, that's the whole secret right there.
Look at it. That tiny little number 2 completely changes the game. It means that speed doesn't just add to the energy, it multiplies it big time. So, back to our car. When you double your speed, you're not doubling the energy. You're multiplying it by 2 squared, which, of course, is 4. And if you were to triple the speed, you'd have 9 times the energy to deal with in a crash. It's this exponential relationship that makes high-speed accidents so devastating.
Now, if kinetic energy is the energy of doing, then its counterpart is the energy of waiting. That's what we call gravitational potential energy. It's basically energy that's been stored up in something just because of where it is, just sitting there waiting for a chance to be released.
Okay, think about this. You lift a heavy bag off the floor. You're using your own energy to fight against gravity, right? Well, that energy doesn't just disappear. It gets transferred into the bag and stored as potential energy. The higher you lift it, the more energy you pack into it. And the second you let go, bam! All that stored potential energy instantly transforms back into kinetic energy as the bag comes crashing down. So we see energy changing from potential to kinetic, and it can go back and forth. This constant transformation, this flow, is all governed by one of the most fundamental, rock-solid laws in all of science. And that brings us to section 3, the unbreakable rule.
And here is that rule, the principle of conservation of energy. What it means is that the total amount of energy in the universe, or in any closed system, is constant. It never changes. You can't just create new energy out of thin air, and you can't destroy it either. All you can ever do is change it from one form to another.
And these transformations are happening literally everywhere, all the time. Energy moves when a force does work. Like when you kick a soccer ball. It flows as electricity through wires to light up your room. It radiates as heat from your morning coffee into the air. It travels as waves, like the light hitting your eyes from this screen right now. Pretty much every single thing that happens, anywhere, is just energy moving from one place or one form to another.
Okay, so we get the basic rules. But how do we take this and apply it on a massive scale? That's section 4, harnessing the flow. We're talking about how we power our entire civilization. When you boil it all down, we basically get the energy we need to run everything from 2 main buckets. You've got your non-renewables, think fossil fuels. These are finite. There's only so much of them in the ground, and when they're gone, they're gone. Then you have renewables. This is stuff like solar and wind, which, as the name suggests, are constantly being replenished by nature.
And here's something that's kind of wild.
Whether you're talking about a coal-fired power plant or a high-tech nuclear reactor, the basic way they make electricity is often exactly the same. It's just a series of energy transfers, a chain reaction. You start with one kind of energy, chemical from coal or nuclear from uranium, and you use it to create heat. That heat boils water into high-pressure steam. The kinetic energy of that moving steam spins a giant fan called a turbine, and that spinning turbine is hooked up to a generator, which finally gives us the electricity we use.
And talking about things on that industrial scale, well, that brings us right to our final section. This is where the clean, simple rules of physics run right into the messy reality of the world. Section 5, our global energy choice.
Because here's the thing. There's no free lunch. Every single energy source has a trade-off. This table really gets to the heart of the problem. Your non-renewables, super reliable. You can pretty much get power from them 24/7, but they pollute. On the other hand, you have renewables. They're clean, which is great, but they can be intermittent. The sun isn't always shining, and the wind isn't always blowing.
Entangled up in all of this is a really critical idea, efficiency. It's actually a pretty simple measurement. It just asks, for all the energy you pour into something, how much useful work do you actually get out of it? And this concept is huge, because even tiny improvements in the efficiency of our cars, or our light bulbs, or our phones, they all add up to a massive drop in how much energy the whole world needs to produce.
But here's the catch. Nothing is perfect. No device is 100% efficient. Because of things like friction or just heat escaping into the air, some energy is always wasted in any conversion. And by wasted, we usually just mean it turns into heat that we can't really use. You know when your laptop gets warm on your lap? That's it. That's the price of inefficiency. That's wasted energy right there.
And that brings us right back to where we started. From the nitty-gritty physics of a car crash all the way up to the global grid that powers our entire world, it's all about energy transfers and trade-offs. The laws of physics, well, they're set in stone. They tell us what's possible, but they don't tell us what we should do. So the final question really isn't a science question at all. It's a question for all of us. What price are we willing to pay?